Video starts with a dynamic animation of a cell, focusing on a gene being transcribed and translated. A voiceover begins. Hey everyone, welcome to Gene Regulation Unlocked. Today, we're diving deep into one of the most elegant and complex systems of gene control in bacteria, attenuation in the TRP operon. You probably already know about the TRP operon's basic function. It's a set of genes that allows E. coli to synthesize its own tryptophan, a vital amino acid. The operon is regulated by a repressor protein. When tryptophan is abundant, it binds to the repressor, which then blocks RNA polymerase from transcribing the genes. Simple, right? But what happens if tryptophan levels are low, but not zero? The cell needs a more nuanced way to fine-tune its response. This is where attenuation comes in. Animation shows the TRP operon with its parts labeled regulatory gene, promoter, operator, leader sequence, L, and structural genes, AE. Attenuation is a secondary or fine-tuning mechanism of regulation that relies on the leader sequence of the TRP operon, located right before the structural genes. This leader sequence is a short stretch of DNA that contains 4 key regions, or domains, that can form specific base pairings with each other. These pairings are the secret to attenuation. Animation highlights the 4 regions of the leader sequence, labeling them 1, 2, 3, and 4. This leader sequence also contains a small stretch of DNA that codes for a very short polypeptide called the leader peptide. Crucially, this leader peptide contains 2 adjacent tryptophan codons. Animation shows a cell with a high concentration of tryptophan. RNA polymerase begins transcribing the leader sequence. Imagine the cell is rich in tryptophan. RNA polymerase starts transcribing the TRP operon. As soon as the leader sequence is transcribed into mRNA, a ribosome quickly binds and begins translating the leader peptide. The animation shows a ribosome moving along the mRNA, synthesizing the leader peptide. When it reaches the 2 tryptophan codons, it finds plenty of tryptophan tRNAs. Because there's a lot of tryptophan available, the ribosome moves smoothly and quickly, without any stalling. It zips right past the 2 tryptophan codons and continues to synthesize the leader peptide. The animation shows the ribosome moving into domain 2. This prevents domain 2 from pairing with domain 3. Instead, the downstream domain 3 pairs with domain 4. This forms a hairpin loop structure known as the attenuator hairpin or the terminator loop. The animation shows the 3-4 hairpin loop forming. This 3-4 loop is a classic row-independent transcription terminator. When RNA polymerase encounters this strong hairpin structure, it stalls and then falls off the DNA. Transcription is terminated and the operon's structural genes are not transcribed. The cell has successfully attenuated gene expression because it doesn't need to make more tryptophan. Animation shows a cell with a low concentration of tryptophan. RNA polymerase begins transcription. Now let's look at what happens when tryptophan is scarce. Again, RNA polymerase starts transcribing the leader sequence. A ribosome hops on and begins translating the leader peptide. The animation shows the ribosome reaching the 2 tryptophan codons, but this time it stalls because there aren't enough tryptophan tRNAs available. This time, when the ribosome gets to the 2 tryptophan codons, it stalls and waits for a tryptophan tRNA to become available. This stalling is the critical step. The animation shows the stalled ribosome now physically blocking domain 1. This allows a different pairing to form. Because the ribosome is stalled over domain 1, it allows domain 2 to pair with domain 3. This forms a different hairpin loop structure known as the anti-terminator loop. The animation shows the 2-3 hairpin loop forming. The formation of this 2-3 loop is the key to preventing attenuation. This hairpin does not act as a transcription terminator. In fact, it's a relatively weak loop that allows RNA polymerase to continue transcribing. RNA polymerase moves past the leader sequence and transcribes the structural genes, allowing the cell to produce the enzymes it needs to synthesize more tryptophan. The animation shows RNA polymerase continuing transcription of the TRP structural genes. This elegant system allows the cell to sense the precise concentration of tryptophan. If it's too high, transcription is terminated early. If it's too low, transcription proceeds. It's a perfect example of how cells can use a single mRNA molecule to make a rapid, sophisticated decision about gene expression. Video ends with a quick summary and a graphic showing the two scenarios side by side. So there you have it. Attenuation is an ingenious way to control gene expression by linking transcription and translation. It's all about a race between the ribosome and RNA polymerase, a molecular dance that fine-tunes the cell's response to its environment.